Last time we discussed how to predict the type of hybridization in a molecule and the electronic geometry, which is the arrangement of hybrid orbitals inside the molecule. The prediction of the actual molecular shape is going to depend only on the atoms of that molecule. The lone pairs in this case are not going to contribute to the molecular shape. For example, a molecule like ammonia, in this case, if you count the number of domains in that molecule, you will clearly see that you have 3 terminal atoms plus 1 lone pair. So that's a total of 4 domains, which means you have sp3 hybridization. sp3 hybridization means that you have a tetrahedral electronic geometry as shown in this figure right here. However, lone pairs doesn't contribute to the shape. The shape of the molecule is going to be only determined by the atoms that form the molecule. And if you closely look at the atoms themselves and ignore the lone pair, you will clearly see that these atoms assume a trigonal pyramidal shape with the central atom a little bit out of the plane of the 3 terminal atoms in this shape right here. So the actual shape of the molecule is not tetrahedral, it's instead is a trigonal pyramidal shape. Despite the fact that lone pairs doesn't determine the shape, is going to be controlling it. If we start from a compound with 2 terminal atoms around the central atom, you will see that the number of terminal atoms are 2, number of lone pairs are 0, which means you have 2 domains in total. And for 2 domains, the electronic geometry is going to be linear with 180 degrees angle between the hybrid orbitals. And since those hybrid orbitals, both of them are used for bonding, the molecule itself will assume the same linear shape. An example for that is beryllium chloride. You can clearly see that you have only 2 domains that will assume the minimum repulsion by assuming the maximum angle of 180 degrees between the terminal atoms. If we have 3 domains around the central atom, in this case, the electronic geometry of the hybrid orbitals or of the electronic domains will assume the maximum angle in order to exhibit the minimum repulsion by assuming the trigonal planar shape with 120 degrees angle. If all of these orbitals are used in bonding, it's gonna lead to a molecule with the same shape, with trigonal planar shape, like boron trifluoride as an example. But if in another case, you have a molecule that uses only 2 domains for bonding and 1 domain for a lone pair, in this case, the electronic geometry is still trigonal planar, but the actual shape is going to be determined only by the atoms. Lone pairs is not going to contribute to the shape. So if you look at the molecular shape in this case, is going to be bent. And you can indicate this on paper by drawing the low structure like this, with the 2 terminal atoms in adjacent positions with respect to each other with an angle that is smaller than 120 degrees. Because the repulsion between lone pairs and bonding pairs is going to be larger than the repulsion between bonding pairs and each other. And that's due to the fact that bonding pairs is kind of restricted in space in between the bonded atoms in comparison to the lone pair, which is extended in space. So it needs to occupy larger space in comparison to the bonding pairs. So as a result of that larger repulsion of the lone pair with bonding pairs is gonna cause the angle to get smaller than 120 degrees. If we have 4 domains around the central atom, as we learned previously, that's gonna result in an sp3 hybridization, which is gonna assume a tetrahedral electronic geometry between the hybrid orbitals with an ideal angle of 109.5 degrees. If all of these 4 orbitals are used for bonding, the molecule will assume the same shape, a tetrahedral shape. An example for that is methane, in this example here, with an angle between the hydrogen atoms of 109.5 degrees. But if the central atom is only using 3 domains in bonding and a lone pair, in this case, the shape is going to be determined by the atoms only. Lone pairs is not going to contribute to the shape. And in this case, the shape is going to be a trigonal pyramidal shape with one of the positions in the tetrahedral occupied by the lone pair. So that means that the angle between the atoms is going to be ideally 109.5. However, it's going to be smaller than 109.5 because, as we said previously, repulsion between lone pairs and bonding pairs is larger than repulsions between bonding pairs and each other. So that's going to cause the angle between bonds in this structure get a little bit smaller than 109.5. Third case, if the central atom is only using 2 domains for bonding and 2 domains are occupied by lone pairs. In this case, shape is going to be only determined by the atoms alone, and it's going to be a bent shape. So that bent shape in this case is gonna have an angle that is ideally 109.5. However, as we said, it's gonna be smaller than 109.5 because again, the repulsion between lone pairs and each other is larger than the repulsion between lone pairs and bonding pairs, which is in turn is larger than the repulsion between bonding pairs and each other, which is going to cause the angle between the bonds to get smaller than 109.5. It's exactly, in case of water, is 104.5. And water is an example of that case or that geometry in this case. So just to emphasize this fact here, lone pairs is not going to contribute to the shape, however, it's going to affect it. So for sp3 molecules, they have 4 sp3 hybrids around the central atoms, but depending on the number of lone pairs that occupies some of these hybrids, the shape is going to be different. If the central atom is using all domains in bonding, it's going to assume the same tetrahedral shape, like in case of methane. If it's only using 3 domains in bonding with 1 lone pair in the 4th position, it's going to assume a trigonal pyramidal shape with an angle that is slightly smaller than 109.5. If it uses only 2 domains in bonding and 2 domains occupied by lone pairs, the actual shape is going to be only determined by the atoms, the oxygen and hydrogen atoms, which is going to make it bent. However, it's bent because of the existence of these 2 lone pairs in this case in water, and the angle is going to get even smaller because of the different repulsion between lone pairs and bonding pairs. For steric number 5 or 5 domains around the central atom, as we learned, that is going to be an sp3d hybridization with 5 hybrids. that are gonna assume a trigonal bipyramidal shape with 3 equatorial domains and 2 axial domains. And if the molecule is using all these 5 domains in bonding, it's gonna assume the same shape in the molecule, like PCl5, that's gonna have a trigonal bipyramidal shape. If it's only using 4 domains in bonding and 1 lone pair, that lone pair will prefer to occupy one of the equatorial positions rather than the axial positions, because it's gonna feel a little bit less repulsion because of the angle with adjacent orbitals. So if you compare a lone pair in the axial position, it's gonna actually feel more repulsion because of the 90 degrees angle with the surrounding orbitals. But if the lone pair is in an equatorial position, it's gonna feel less repulsion because of the 120 degrees angle with adjacent orbitals. And that is gonna result in what is called a seesaw shape in the molecule. An example for that is SF4 molecule is gonna have a seesaw shape. If the central atom is using only 3 domains in bonding and 2 are occupied with lone pairs, again, second lone pair is gonna prefer one of the equatorial positions, and that is gonna result in a T shape for the molecule, like the case in ClF3 molecule. The molecule is only using 2 domains in bonding with 3 domains occupied by lone pairs. That molecule is gonna assume a linear shape because the bonding pairs are gonna occupy the axial positions at 180 degrees angle with respect to each other, and the lone pairs are gonna occupy equatorial positions to exhibit the minimum repulsion possible due to the 120 degrees angle between each one of them. An example for that is xenon difluoride. The last steric number is steric number 6, which means you have 6 domains around the central atom, 6 hybrid orbitals, 6 sp3d2 hybrid orbitals that are gonna exhibit an octahedral arrangement or an octahedral electron geometry with 2 of them oriented along each axis, 2 along z axis, 2 along x axis, and 2 along y axis, with an angle of 90 degrees between each 2 of them. And if the molecule is using all of the 6 domains in bonding, it's going to assume the same shape, an octahedral shape. An example for that is SF6. But if it's using 5 domains in bonding and 1 occupied by a lone pair, it's going to be any one of them because all these positions are identical. So it's not going to make a difference for the lone pair to occupy any one of them. And the result is going to be a tetragonal pyramidal shape. An example for that is BRF5 molecule. If the molecule is using 4 domains in bonding and 2 domains occupied by lone pairs, the second lone pair is gonna want to be in the opposite direction to the already existing lone pair to minimize the repulsion by assuming a 180 degrees angle with the already existing lone pair. So the overall shape of the molecule in this case is gonna be square planar shape, and an example for that is xenon tetrafluoride. And that table here kind of summarizes all the possible variations of molecular shapes based on the number of lone pairs in the molecule.